Hi everyone, my name is Gus Campbell. This is my submission for Lab 1. Let's get started. So for introduction, for Lab 1, which is also called charge tapes, we are tasked to demonstrate the movement of charge through contact through pieces of clear tape. As we learn about charge as polarization, this lab intends to use household objects to show an important property of matter/electricity. There's really two main physical concepts for this lab. One being the idea of the motion of charge by contact, and the other being conservation of charge. Both of those were introduced kind of in the second week. So getting into the lab itself, these are the materials I used. You can see there's the roll of tape, and then the measuring tape, which had millimeters down to it. And then hanging off the desk there was the two pieces of tape themselves. The length of tape that I ended up using was about 20 centimeters. That was kind of the best balance of rigidity and usability, and then being able to hang, and we can see clear results later on in the lab. This is me in the process of making the U-tapes. The U-tapes is how I'm going to talk about those from this point on. In this example, we're taking tape, we're creating positively charged tape, while the net charge on both pieces of tape stays the same because of the mobile charges being electrons staying on the base piece of tape. We end up, after tearing these two pieces of tape apart, we end up with a positively charged U-tape and a negatively charged base tape. But in this example, we're going to only talk about the positively charged U-tape. After doing this, we wanted to interact with it with other objects to see kind of how it reacted and make sure that it is in fact positively charged. So I interacted it with my hand, and after some polarization of my hand, it did find some attraction to the hand. And then specifically, we wanted to test a negatively charged object. So we took a plastic pencil, we rubbed it against some cloth to create a negative charge, and there was a definite, clear, defined attraction. It's safe to assume that if the U-tape was negatively charged, it would repel, but in this case, it was a positively charged piece of tape, so there was the attraction there. It's also safe to assume that if the U-tape was neutrally charged, after some time there would be some polarization, there would also be some attraction, but it wouldn't be as well pronounced as it was in this case as being positively attractive. For the final part of the experiment itself, we wanted to see if we could make two pieces of U-tape repel each other to the point that one overcomes the forces of gravity and floats. We're going to have to make some assumptions going into this. The first one being that the two pieces of U-tapes were created the same way, which I believe I was able to accomplish, and that they have the same charge in that sense. And then we can treat that for the calculations, we can treat the charges on the tape as point charges in the center of the tape due to the uniformity of the charge throughout. So from this point on, we're going to assume those things. I apologize for the poor images here, but after some multiple tries of this experiment, I was able to find pretty consistent results in the fact that the tape would float and would kind of levitate and repel off each other in about 2 millimeters apart. I know this isn't a great picture, but as I repeated the test multiple times, and that was about the point that I could see there's separation. You could start to see kind of an interaction about 2.5, 3 millimeters, but as we're moving it around, you could see that it was floating about 2 millimeters above. So I wanted to show a free body diagram of kind of the forces going on here. That's to be shown on the left there. And in this case, there's the assumption of other vertical forces being caused by the polarization of the book and the box shown in the last slide there, or even the table itself. But I believe that those forces are small enough that we can justify them being negligible, and that the force of gravity and the force from the repel of the other piece of tape are significantly larger. So for the sake of calculations, we're not taking those into consideration. And then at this point, we can find the other calculations here. The force of gravity is the mass times the gravitational acceleration. In this case, since we can assume that tape is about 1 gram per meter, and mine were about 20 centimeter pieces, the mass is 0.2 grams, and then gravity is 9.81 meters per second squared, so we find 1.962 newtons. The distance floating we measured as 0.002 meters, or 2 millimeters. And then that's the point charge equation there. We can assume that Q1 and Q2 are the same charge, and then here's the force equation that we used here. Now, since we said that the force of the second, well, actually I didn't say this yet, I apologize. We're assuming that the momentum is the same, that there's no change in momentum on the tape that's floating, which would imply that the acceleration is 0. So we want the force of the repellent from the other tape and the force of gravity to be equal to each other, just negative in this case. Just reverse, I should say, or negative, yeah. So for the equation itself, we ended up putting this, which was this equation, and then times the second q to find force here. And then since these are equal, we can just assume q squared. Set that equal to the gravitational constant, or the force of gravity, I should say. We end up getting this equation excluding any kind of actual numbers. We're going to end up using this in our code, and then this is what we end up finding here, which is q1 equals q2 equals 2.953 times 10 to the minus 9, and that's in newtons. I should have put that, but it is in newtons because it is a force. And that makes physical sense in my mind as well. So moving on to the code. Now going into the code, we're going to make some more assumptions. First off, we're continuing to keep the assumption that all the charge can be calculated as a point charge in the center of the tape, and then the U-tapes are the same. So moving on with that, this is a lot of the same code from Lab 0. I added in a little extra thing to show some physical sense, make sure everything was correct in my mind, and then added some lab-specific constants. But when we run this program, we get our model here. Model being here, where this is the bottom U-tape, this is the top U-tape, this is the force from the repelling of the bottom U-tape, and this is the force of gravity here. The couple first lines here were something for me to see. Assuming the charge was Q, that would be the electric field and the electric force. That's just to make sure that the physical, like, it all makes sense in my mind, because Q is the typical constant we use, and those are very familiar numbers to me, so that makes sense in my mind from a physical standpoint. And then the calculation itself was what I got by hand, I believe. So, and I put newtons here. So making some final comments here, some last minute questions. What if electrons had positive charge and protons had negative charge? We're still assuming that the electrons and the mobile charges here. The calculations would be the exact same. The electrons would still stay in the base tape, so the U-tape would end up being negatively charged. But besides the experiment with the pen, the calculations for the other thing, the U-tape interacting with each other, would be the exact same. It's just the repelling force of two negative charges versus two positive charges. So we'd end up with the same answer here. And then why it's important to handle the charge tape as little as possible, I can attest to this. I had a couple pieces of tape that were end up neutral after I just manhandled them a little too much, as the mobile charges would go into my hand and then into the rest of my body, leaving the tape ending up neutral, and that's not what we want for this experiment. So I'm Gus Campbell. I appreciate your time. This has been Lab 1. Have a great day.